In this video, we are going to be looking at the reactions to synthesize esters and how we're going to be utilizing esters. And in addition, we will be talking about amines. When it comes to the process of synthesis of an ester, the reactants are going to be a carboxylic acid, and an alcohol. This reaction has to happen in the process of acid and heat. And remember that heat is symbolized by the triangle. When it comes to acid, it has to be in strong acid. That's why we symbolize it by H+. In essence, overall, what is going to be happening is that the OH group in the carboxylic acid is going to be combined with the hydrogen atom in the alcohol. And if I highlight those atoms, once they come together, they're going to form a molecule of water. Then the oxygen with its alkyl group will be linked to the carbon that is double bonded with oxygen. And that's how we form an ester. Now that I showed you how to synthesize esters, I'm going to show you how to hydrolyze them. And the reason why we go over hydrolysis is because this is one of the processes that happen in the body in order for fats to be utilized as energy, okay? But it also, a reaction that involves the hydrolysis of esters is very useful in some of the products that you may have at home already. So, when it comes to the hydrolysis of esters, understand that hydrolysis can occur under acidic conditions. Okay, that it will be an acid hydrolysis of an ester. And when that happens, what we're going to have is that an ester is going to react with water, and the product of that reaction is going to be a carboxylic acid and an alcohol. Now, understand that in this whole process, what is happening is that the water molecule, we need to envision it, even though we always write it as H2O, as a source of hydrogen and OH. Because hydrolysis in other words, hydrolysis means cutting with water. And as you can see in the bottom reaction, water is going to be a source of hydrogen and a source of hydroxide. So every time we're doing acid hydrolysis of an ester, you should keep in mind that the actual split of the molecule is going to be occurring between the bond that is a C double bond O. I'm going to highlight it. And the single bond oxygen with its alkyl group. Then, when it comes to this, always the portion that is double bonded to oxygen is going to be linked to the OH. The portion that kept the oxygen receives the hydrogen. That's why we see the two products that we observed. And remember, when we are hydrolyzing an ester under acidic conditions, we form a carboxylic acid and an alcohol. Hydrolysis for esters can also happen under basic conditions. Under basic conditions, we are not going to be using water. Understand that under base hydrolysis conditions, which is also known as saponification, we are going to be using strong base. As you remember from Chapter 10, your strong bases are going to be NaOH, KOH, etc. Remember that strong bases are going to have metals that are in group 1A and 2A, and they're going to be paired with hydroxide. During this process, we need to heat the reaction. The products of base hydrolysis of an ester produce a carboxylate salt, or a carboxylic acid salt, and an alcohol. And similar to what we saw in acid hydrolysis, we're going to be splitting the molecule, okay, where we have the C double bond O and the single bond to oxygen, and whatever alkyl group does it have. Let's practice now how to predict the products given reactions that are going to be either esterification or hydrolysis of esters. So for this, we're going to go through some of the problems that we have on the worksheet. And as you can see, when it comes to these, it is very important that you identify what are the molecules that are given to you. So as you can see on problem A and B, those are going to be esterification reactions, because we have carboxylic acid and alcohol in the process of acid and heat. As you can see, we have a carboxylic acid and an alcohol also on letter B, and we have it on acid and heat. Remember, I'm going to highlight the atoms. Whenever we are esterifying, making an ester, so I should specify we're making an ester. What happens in the whole process is that I am going to be combining the OH group in the carboxylic acid with the hydrogen in the alcohol, and those two groups are going to be making water. Then I'm going to rewrite my carboxylic acid up to the carbon that is double bonded to oxygen. So in the molecule that we have on reaction A, that is going to be 1 carbon, 2 carbon, 3 carbons, double bond to oxygen. And then I'm going to do a single bond to oxygen. Then that single bond to oxygen is bonded to a CH2. And that CH2 is bonded to a CH that contains 2 CH3s. So to highlight the molecules that are here, as you can see, this portion of the molecule is what I drew here. And then we are going to link it to the oxygen atom and the rest of the molecule. So that is this portion. So again, on letter B, we also have an esterification reaction. Here we have the compound that I mentioned before, which is called benzoic acid. And when benzoic acid reacts with, in this case, 2-butanol, this is just reviewing nomenclature. Remember, the OH in the carboxylic acid is going to bind the hydrogen in the alcohol. That's going to make a water molecule. And the product of the reaction is going to be the benzene ring, the C double bond O, bonded now to oxygen. That oxygen is bonded to the methyl group, to an ethyl group on the other side. So that will be the product of the second reaction. So on C, we have acid hydrolysis of an ester. And remember that when we have acid hydrolysis of an ester, we're going to be making a carboxylic acid and an alcohol. Whenever we have this, which must take into account that we're going to cut the molecule here. The portion of the molecule that retains the C double bond O, which I'm highlighted in gray, so that portion of the molecule is going to receive the OH group. Please note that here we also have water doing the reaction, so make sure that you write in the water. So here, this is what's going to turn into a carboxylic acid. And then we're going to write the oxygen, which is going to receive the hydrogen and the alkyl chain that is attached to it. The last reaction that we have here is going to be base hydrolysis. And when we do base hydrolysis, remember that this is going to give us a carboxylate, salt, and an alcohol. When it comes to this, remember, we are going to be cutting the molecule in between the C double bond O and the single bond oxygen. So the alcohol is going to look like OH with a line. Remember that this is methanol. And the carboxylate salt is going to be the hexagon with a carbon that is double bonded to oxygen and oxygen that is negatively charged. And in this case, because we're doing base hydrolysis with NaOH, that is going to be paired with sodium. Now let's talk about amines. Amines are a functional group in organic chemistry that is known to be derivatives of ammonia. Now, understand that when it comes to amines, we are going to have one or more of the hydrogens in ammonia being replaced by an alkyl group or an aromatic group. So, as you can see here, we have 3 different molecules that are examples of amines. Amines can be classified similar to what we did previously to classify alcohols as primary amines, secondary amines, or tertiary amines. Now, when it comes to the classifications of the amines, understand that what makes something primary, secondary, or tertiary is going to be specifically how many carbon atoms are attached to the nitrogen. So, if we look at a primary amine, the nitrogen is going to be bonded to 1 carbon. In a secondary amine, your nitrogen will be bonded to 2 carbon. And in a tertiary amine, your amine is going to be bonded to 1, 2, 3 carbon atoms. When it comes to amines, you guys are not responsible for the IUPAC naming of amines. You are going to be naming amines according to their common names. And similar to what we did previously to main ethers, the way that we name an amine is by looking at the alkyl group that are going to be present in the molecule, and we're going to use them as prefixes. So, for example, the first molecule that we have is an ethyl group bonded to nitrogen, so that's why the name is ethylamine. The second molecule, we have two methyl groups attached to a nitrogen, that's why the name is dimethylamine. Lastly, in the last amine, we have a methyl, another methyl, and an ethyl group. Remember that if we have substituents that are multiples, we must use the prefixes to determine how many we have, and we need to put our substituents in alphabetical order. Remember, the prefix di, tri, tetra is not alphabetized. So the correct name for that last molecule is going to be ethyl dimethylamine. Now, we have seen in Chapter 11 already discussions about aromatic amines. And when it comes to aromatic amines, we already know that if we have a benzene ring bonded to an amino group, that is known as aniline. Okay? So, when we are naming anilines, one of the things that we did not establish back in Chapter 11 was what happens if now my substituent is bonded to the nitrogen in aniline? Well, when we're naming those molecules to symbolize that the substituent is on the aniline, then we're going to utilize the letter N to say that our substituent is bonded on the nitrogen of the aniline. But the longest carbon chain in these molecules is always going to be the aniline motif. That's why the last word of the molecule is going to be aniline. And since we have a CH3 group on the nitrogen, that's why it's N-methylaniline. So, as you can see in the third example, this is going to be similar to how we learn to name aniline molecules in Chapter 11. Here we have a chlorine that it is bonded to the benzene portion of aniline. Remember that when we have that, carbon number 1 is going to be the carbon in the benzene ring that is attached to the amino group, and then we're going to number the cyclic system or the benzene clockwise or counterclockwise to give the substituents the lowest number. So in this case, we need to number this ring clockwise. So this is position 2, position 3, 4, 5, 6. That's why the name of this compound is going to be 3-chloroaniline. So aniline is actually a very interesting molecule because it is used to make many dyes. And the reason why we have blue jeans is because of the compound of aniline. Now let's practice naming amines or aniline derivatives. So I'm going to do all 3 problems on the worksheet. And in the first one, we have an amine. On the second one, we have an aniline derivative. And in the last one, we have another amine. Remember that aniline, I just want to specify that that is just an aromatic amine. So aniline is an amine. So when it comes to this, as we can see here, we have 1, 2, 3, 4 carbon atoms bonded to an NH2. So we only have one substituent. So in this case, we have 1 butyl amine as the name of that compound. In the second molecule, as you can see, we have an ethyl group. Just remember that there's a carbon right here, there's a carbon right here. And we also have an ethyl group on the ring. So when it comes to this, remember, your longest carbon chain is going to be the aniline motif, which I highlighted in magenta. So that is the last word in the molecule, aniline. We have two substituents that are the same. So this is diethyl. Now, one is located in the nitrogen, the other one is located in the ring. Remember that when we're numbering the ring, the carbon that has the amino group is going to be number 1. In this case, we need to number it clockwise. And the locations of those ethyl groups is going to be N and also number 3. So the correct name of that second molecule is N,3 diethyl aniline. And we are always going to put, in the case that we have the same substituent on the nitrogen and within the ring, we're going to put the N first before the number. If we look at the last amine, we are going to have two substituents that are the same, methyl and methyl, and we have an isopropyl group. We have a methyl group here, a methyl group here, and this whole thing is an isopropyl. So the name of the last compound, we have to end with the word amine. I'm just going to erase the classification. So this is going to be amine. And then we're going to put our substituents in alphabetical order. So this is isopropyl, dimethyl, amine. Because remember, the di does not get alphabetized. Now let's move on to talk about the solubility of amines. Amines are going to be molecules that can undergo hydrogen bonding, not only with themselves, but also with water molecules. Understand that primary and secondary amines with fewer than 6 carbons are soluble in water, okay? And they're soluble in water because they can form hydrogen bonds with water molecules. Remember that hydrogen bonding is fun, meaning that the hydrogen atom has to be bonded to fluorine, oxygen, or nitrogen. And in the case of primary and secondary amines, they will be able to undergo hydrogen bonding with water molecules. Now, tertiary amines can form hydrogen bonds only with water molecules. They cannot form hydrogen bonding with themselves. Because if we look at the structure of tertiary amines, and I'm just going to draw the structure of trimethylamine. So we have CH3 bonded to nitrogen, CH3, 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 CH3. The reason why no H bonding is observed between two molecules that are tertiary amine is because if we look at the molecule, the hydrogen is bonded to the carbon atom. So remember, if you have amines of more than 6 carbons, the effect of hydrogen bonding is diminished. At that point, the nonpolar portion of the hydrocarbon chains are going to decrease the solubility of the amine in water. Amines are actually bases, and I just want you guys to remember that, because we know that ammonia is going to be a weak base. Amines are also weak bases. So if we put them in water, they are going to have a reversible reaction in which the amine is going to then act as a base. Water is going to act as an acid. And as you can see, that base gets protonated. That acid loses a proton. But this reaction is not very favorable and it reverses rapidly. Amines are not only straight chains, they also are heterocyclic. So heterocyclic amines is that within the cyclic system, nitrogen, it is part of the structure. So in this slide, we have examples of heterocyclic amines. I do not require you guys to memorize these structures. The only reason why I bring them up is because we're going to look at some biomolecules in the area of biochemistry that contain these structures. Just understand the basic definition of a heterocyclic amine, which means that we're going to have a ring system that has nitrogen as one of the atoms in the cyclic molecule. One of the things where we see this heterocyclic amines in action are when it comes to alkaloids. Understand that alkaloids are going to be physiologically active compounds that are produced by plants, and they have this heterocyclic amines. They are used as anesthetics, they're used in antidepressants, they're actually even found in stimulants, and they're known to be habit forming. Now, to give you guys some examples of alkaloids, here we have the structure of nicotine, which is in the top, and the structure of caffeine. Maybe some of you utilize any of these products. Now, the main thing that I want to specify when it comes to this is that you guys should know what is an alkaloid by the definition. You don't need to identify the heterocyclic amines or how many are present, but just know the definition of an alkaloid.